Welcome to Numerical Analysis. Today we are diving into one of the most crucial concepts in computational mathematics, the rate and order of convergence. Whenever we use a computer to approximate a solution, we want to know how fast we can get to the correct answer. Understanding this speed is what separates a good algorithm from a truly great one. Let us begin our journey. Now that we know our topic, let us understand what convergence actually means. Imagine you are trying to guess a secret number between 1 and 100. Every time you guess, I tell you exactly how far off you are. That distance is your error. As you make more guesses, your error shrinks and you get closer to the truth. In numerical analysis, this process of approaching the exact answer step by step is called convergence. But why does this matter? Because not all guessing strategies are equal. Some shrink the error slowly, like walking, while others shrink it incredibly fast, like a bullet train. To truly analyze these strategies, we must define this concept mathematically so we can measure it. Suppose the exact true answer to a math problem is a number we will call x star. In any numerical method, we generate a sequence of guesses. We call our current guess x sub n, where n represents the current step number. The absolute difference between our current guess and the true answer is the error at step n, written as e sub n. If our numerical method works correctly, this error gets smaller and approaches 0 as n gets larger. This brings us to the core mathematical definition of how fast a method converges. To measure the speed, we compare the error at the next step to the error at the current step. This limit formula shows that the next error is proportional to the current error raised to some power p. Let us break down these symbols. The term e subscript n plus 1 is the error at the upcoming step. The exponent p is a strictly positive number called the order of convergence. You can think of p as the type of engine driving our method. The letter c represents the asymptotic error constant, also known as the rate of convergence. This constant c tells us the horsepower of that specific engine. Now that we have our formula, let us look at the two most common types of engines, or orders of convergence. When the order p is equal to 1, we call it linear convergence. This means the error decreases by a constant fraction each time. It is steady and predictable. However, when p is equal to 2, we call it quadratic convergence. This is where things get exciting. In quadratic convergence, the new error is proportional to the square of the old error. Because the error is typically a small decimal, squaring it makes it drastically smaller, leading to incredibly fast results. Before we move on to a concrete example, we need a version of our formula that we can actually compute. The limit equation we just saw strictly holds true only as the number of steps approaches infinity. But in practice, we are looking at a specific step. So we drop the limit and treat the relationship as an approximation. This gives us a direct equation to estimate the next error based on the current error, the rate constant c, and the order p. This practical formula is incredibly useful because it allows us to predict how the error behaves without ever needing to know the true answer. Let us see this practical formula in action with a basic numerical example. Suppose we are using a specific numerical method and we know that our current error at step n is 0.1. We are told that this method has linear convergence. As we learnt earlier, linear convergence means the order p is exactly 1. We are also given that the rate constant c for this method is 0.5. Our goal is to find the expected error at the very next step. To solve this, we will use the asymptotic error approximation formula we just defined, setting up our known values. Continuing with our calculation, we substitute the given values into our general error formula. We replace the current error magnitude with 0.1, the rate constant c with 0.5, and the order p with 1. Calculating this simple arithmetic, we find that the new error is 0.05. Notice that this new error is exactly half of the previous error of 0.1. This halving behavior is the hallmark of linear convergence with a rate of 1/2. It shows steady, predictable progress toward the true solution, much like the bisection method. Now let us examine a more powerful method to see the impact of a higher order. Suppose another numerical method has the exact same initial error of 0.1 at step n. However, this method features quadratic convergence, meaning its order p is 2. The rate constant c for this specific method is given as 1.0. We want to find the expected error at the next step to compare it with a previous linear method. Our strategy remains exactly the same. We will use the general asymptotic error approximation formula, which acts as a mathematical bridge from the current step to the next. Let us finish this calculation by inserting our specific parameters. The current error remains 0.1 and the rate constant is 1.0. The crucial difference is that our order power p is now 2. Squaring the current error of 0.1 is the critical mathematical operation happening here. The result shows that the new error has plummeted to 0.01. By squaring the previous error, the method has drastically reduced the distance to the true answer. This massive drop illustrates the immense power of quadratic convergence compared to linear convergence, requiring far fewer steps to reach high accuracy. To truly appreciate what we just calculated, let us look at this visually. Here we have a graph comparing linear and quadratic convergence. The vertical axis represents the absolute error on a logarithmic scale, meaning each tick mark is 10 times smaller than the one above it. The horizontal axis shows the number of iterations. The gently sloping blue line represents a linear method, where the error decreases at a steady, constant pace. In stark contrast, the steeply dropping red curve represents a quadratic method. Notice how the error collapses rapidly as it squares itself, reaching the bottom of the graph in a fraction of the steps required by the linear line. Why does understanding this graph matter in the real world? In modern engineering, we rarely solve just one equation. We often solve systems with millions of complex equations, such as simulating airflow over an airplane wing. If an engineer chooses a linear method, it might take 1,000,000 steps to reach an acceptable error, consuming days of expensive supercomputer time. However, a quadratic method might reach that exact same accuracy in just 10 steps, finishing the job in mere seconds. Understanding the order of convergence allows engineers to choose the most efficient algorithm, preventing massive wastes of time and electricity. We have covered a lot of ground today, so let us summarize the most important ideas. First, convergence measures how successfully a numerical method approaches the true, exact solution. Second, the order of convergence dictates the fundamental speed class of the method, such as linear or quadratic. Third, the rate constant provides the specific speed multiplier for that particular class. Ultimately, higher order methods destroy mathematical error much faster, saving massive amounts of computational resources. You now have the foundational understanding to analyze the efficiency of any numerical algorithm.